Okay, so finally we come to the last section in this chapter on angular momentum in multi-electron atoms. And this is when we finally get to multi-electron atom term symbols. So let's sort of dive in. This is a good enough slide than to dive in. So remember that back in the chapter on hydrogen atom, we looked at the fine structure, and one of the terms that we had to add to improve the energy levels for the hydrogen atom was the spin-orbit coupling, which is this correction to the Hamiltonian. So if I write my Hamiltonian, then in terms of three terms, let's just take H naught as sort of the Hamiltonian if I would have if I had just non-interacting electrons and I ignored all the other interactions. And then it would just be the attractive force to the nucleus, and then the attractive force to the nucleus, and then the kinetic energy for that electron. So there's n electrons, and we sum over all of them. But now we have to add in, for a multi-electron atom, we have to add in the repulsion between all the electrons, which is this term here. And if we now include the spin-orbit coupling, then for all the electrons, there's a coupling between its orbital angular momentum and its spin angular momentum, and there's a coupling, associated coupling constant for each of them. So now we have three terms in our description of a multi-electron atom. And each of these guys is a sum over all of them. Now, there are other terms too that you can add, but we're going to stick with these guys. The rest of them can be added as perturbations to this. All right. Now, if you don't have any fields present, no electric fields or sort of external electric fields or external magnetic fields, then we can leave this guy just sort of written in terms of three terms here. And what we saw in the hydrogen atom case was that this term was pretty tiny compared to the H naught term here, which was the hydrogen atom problem that we solved. And what we also see, if we were looking at helium, we'd find that the spin orbit term was also pretty small compared to this electron-electron repulsive term that we saw in the helium atom. So in general, for atoms which have a low number of electrons, we find that the spin orbit term can usually be treated as a small perturbation on these two terms. So we're going to define our zeroth order Hamiltonian as just H naught and the repulsion Hamiltonian. So the non-interacting Hamiltonian, and then adding in the repulsion term for atoms just for n less than 40. Okay, and when we get to beyond this, what we find is that if you remember when we derived the spin orbit coupling, remember that we saw that the spin orbit coupling constant went as z to the fourth, and z to the fourth means that this starts to increase pretty quickly. So when you get beyond n equals 40, you get to a situation where now the spin orbit coupling starts to get much larger than this term, and so we have to change our zeroth order Hamiltonian to be the non-interacting Hamiltonian plus the spin orbit coupling term, and then we'll treat the electron-electron repulsion as a perturbation onto that guy. But we're getting ahead of ourselves. What I'm going to do is focus mainly on this case right here, and we'll just touch on that very briefly later on. Okay, so we're going to look at low Z multi-electron atoms, and by low Z I mean Z less than 40 or less. So in this case, then, we're going to find it's very convenient to first add up all the individual electron orbital angular momenta to make a total orbital angular momentum, L. And then we're going to add up all the individual electron spin angular momenta to make a total spin angular momentum, S, capital S. Okay? And likewise, for each one of these guys, there'll be a Z component. So the LZ component will have an eigenvalue which is ML, capital ML, H bar, and this capital H ML is going to be the sum of all the individual MLs for the electrons. And the same for SZ component. So there'll be an eigenvalue of MS H bar, and that MS quantum number is going to be the sum of all the individual electron MS values. All right. Now the total angular momentum, we're going to write then is just the sum of L and S. And what we'll find is that the total angular momentum, as you might expect, the total angular momentum is going to commute with the whole Hamiltonian, but it also commutes with the 0th order Hamiltonian there. So that's clearly a constant motion in this system. But in the Losey case, with these definitions, we'll also find that the orbital angular momentum, total orbital angular momentum operator, commutes with H0, and the total spin angular commutes with H0. So this means that both these guys are also separately conserved, that they're invariant under the motion of the system. So that's useful, okay? Now this is all assuming that we've neglected the spin-orbit coupling. Now if we bring in the spin-orbit coupling, it will start to mess with this a little bit, but we're going to bring it in as a small perturbation. So this limit is what's called the Russell-Saunders coupling limit, or the LS coupling limit. So the idea is that you couple all the L's, individual L's first to make a big L, all the individual S's to make a big S, and then you couple big S and big L and big S together to make total J. So that's called LS coupling. All right. And once we know the big L, the big S, and the big J, then we can start talking about atomic term symbols for multi-electron atoms. So when we get to multi-electron atoms, then we're going to have a symbol completely analogous to what we saw in the hydrogen case, where we're going to have some symbol for the total orbital angular momentum, which is going to be either S, P, D, F, G, so on, based on the value for total L. We're also going to have a multiplicity, which is going to be 2 times capital S plus 1, so the total spin, and that's going to be up here as a superscript. And then the total angular momentum, quantum number J, will be down here as a subscript, okay? So exactly what we did in the hydrogen atom, but now it's going to involve the total orbital spin and total angular momentum, all right? All right, so let's jump right in, take a quick example here. What if we have a 1s2 configuration? What's the term symbol for that? Okay, so if I wrote down what we know about that system, well, we know that m sub L is equal to 0 for the first electron, and this m sub S value would say equal to half. The second electron has an m sub L equal to 0, and of course, Pauli's exclusion principle tells us this one has to have an m sub S value of minus half. And if I calculate ML total, 0 plus 0 gives me 0. If I calculate MS total, I get half plus minus half equals 0. So that tells me that whatever the term that's associated with this configuration, it has to have m sub L of 0 and m sub S of 0, and that's all we have. Now, if you're looking at that and you're thinking, well, how could I get that possible outcome? Well, there's only one way of getting m sub L, only one m sub L of 0. That is that you must have a total L of 0. And there's only one way of getting a total m sub S of 0, which you must have a total S of 0, or a multiplicity of 1, 2s plus 1. So the total J, which is going to be L plus S, is also going to be 0, and clearly you're only going to have one mj value allowed in this case, which is m sub j. So for the term symbol, we have everything we need. We know S, total L, total J, all of them are equal to 0. So this becomes a singlet S0 state. All right. So in a way, this is kind of like a puzzle that we're working backwards. Given this information, which is the electron configuration, and working backwards to figure out what are the possible S, L, and J values, and then get the term symbol. And this is probably the simplest of the puzzles. We'll make the puzzles get a little harder here. All right. So let's try 2p6 configuration. All right. So if this is the configuration we're talking about, then you can right away see that if I calculated the total ms, well, that's plus half minus half, 0, plus half minus half, 0, plus half minus half, 0. So the whole thing adds up to 0. And m sub L, well, there's minus 1, there's 1, 2 of those, so that's minus 2. There's 2 of zeros, but then there's 2 of plus 1, so that makes minus 2, 0, plus 2 adds up to 0. That's the outcome. Only one possible way solution you get. So clearly, again, this is just like before. There's only one solution, so you must have total S equals 0, total L equals 0, and of course total J equals 0. This is also a singlet S0 state. Right? Now, all the subshells that are going to be filled, we're going to be able to ignore in this picture. So that's going to be a simplification. So like if I had done the same thing, but I gave you the full electron configuration, you'd have to do the same thing again. You'd get, here's the M sub L values, you'd get the M sub S values here, you'd have to add it all up, but you'd get up with the same result. So anytime you have filled subshells or shells, then you can just ignore them because they're just going to contribute, they're all going to be singlet S0 states. Right? So those are sort of the easy ones, right? Okay, so all the closed shells and subshells are singlet S0s. Let's try another one here. Let's try a helium configuration where one of the electrons is in the excited state of a 2s orbital. So we have a configuration that's 1s1, 2s1. Now we have some flexibility, some ways in which we could vary in how we place our electrons in these orbitals in their spin states, right? So take a look here. Then we can have one electron in the 1s in the spin up state, one electron in the 2s in the spin up state. And if we looked at that state, well, this is, both of these guys are M sub L equals 0, so the total is always going to be M sub L for 0 for any possibility. But for the M sub S, this is plus half, that's going to give us a total of M sub S equals plus 1, right? And then when we get to the next possibility, well, that possibility is that spin is up in 1s and down in 2s. So that actually gives us a total ms of 0. Of course, M sub L is also equal to 0. And then if we do the next possibility down for 1s and up for 2s, well, that again is going to give us M sub S is 0, and M sub L, of course, is 0. And then the last possibility is down in 1s and down in 2s. That's going to give us a total M sub S of minus 1, again with M sub L equals 0. And then we can add these guys up to get the M sub J's. And so we have 1 plus 0 equals 1 for M sub J. 0 plus 0 equals 0. 0, 0 gives you 0, and minus 1 and 0 gives you minus 1. So here's our possible values of M sub S, M sub L, and M sub J. So now, here's the question. What are the values of capital L, capital S, and capital J, all of them, that the possibilities that would give you this result, right? So all states have M sub L equal to 0. So clearly, total L has to be equal to 0. So check, that one's figured out, all right? The highest M sub S value that we see is plus 1, and the lowest is minus 1, and then we see some zeros in there. So clearly there is a state that's associated with, has ms of minus 1, 0, and plus 1. That tells us that there must be an S equals 1 term in this possibility here. So we know that only L equals 0 is possible, but there's evidence here for an S equals 1. And that takes out 3 states, right? That means that of the 4 states, 3 are associated with S equals 1, which leaves 1 state left over, which has to have M sub S equals 0, M sub L equals 0. That has to belong to an S equals 0, and finally that means we're going to have a J equals 0, because they're all L equals 0. All right, so this leads to then 2 configurations. We have L equals 0, S equals 1, gives us a total J equals 1. That's going to be a triplet. Remember, 2S plus 1 is a triplet. Capital S, because we have L equals 0, and then J is 1, so that's our subscript. So triplet S1 is one of the states. And then the other state is this last one here, which is going to be L equals 0, S equals 0, J equals 0. That's going to be a singlet S0 term. All right? So that one was a little trickier. But now you sort of see it's sort of a bit of a game where you have to try to figure out all the possible capital S, L's, and J's that can be responsible for all those ways in which you can put together the electron configurations. Now, when we put spin-orbit coupling back into the picture, then what we saw, if you remember way back into the chapter on the hydrogen atom, we saw that J was what we needed to look at for to determine the actual energies, and that spin-orbit coupling actually lifted the degeneracy between the different J levels. So without the spin-orbit coupling, all the J values were different, all had the same energy, but once you add in spin-orbit coupling, the J values will then have different energies. So what we're going to use is something called Hund's rule, which will allow us to look at the terms, and based on the terms, figure out which one's the ground state configuration. So as you put those electrons, if you go back to this picture here, and you look at this, you might ask, like, which one of these is the lowest state, which one's the highest state, energy state. And you'll have to stare at this for a while, but you might not get it. But if we look at Hund's rule tells us that the term with the highest multiplicity, 2s plus 1, is the lowest in energy. So term energy increases with decreasing multiplicity. So what did we see? The highest multiplicity term was the triplet S1. So that was the lowest energy term symbol, and the singlet S1, S0 was the higher energy one, okay? And then for terms with the same multiplicity, which we didn't see in the last case, the term with the highest L is going to be lowest in energy. And then if you get into a situation where you have multiple terms that have the same value of L and S, then the terms that are associated with less than half-filled subshells, then the ones that have the smallest J are going to be lowest in energy, and the ones that have more than half-filled subshells, then the terms with the largest J are going to be lowest in energy. So those are the rules. There's 3 rules and 2 sub-rules down here. We'll look at an example where we have to deal with all of this, okay? So here's the tough one, carbon. We have a 2p2 configuration. So you want to put 2 electrons in 3 orbitals, but remember they can be up or down, so there's really 6 spin orbitals that we're talking about here. So we're going to use just combinatorics here to tell us that the ways in which you can arrange n electrons in g orbitals can just be calculated, and that tells us that there should be 15 possible ways of doing this. Now, if you don't follow that, you may want to do a review of permutations and combinations, and I'll just look on Wikipedia or Google it around. But don't worry. If you don't worry, I mean, the other way of doing it is to just by trial and error make sure you've elucidated all the possible values, and that's what I've done here. So you see here, then I've said I got 3 p orbitals, but I can put an electron either up or down in each of them. So there's 6 possibilities for how I can make an arrangement. That's what that 6 here represents, all right? And there are only 2 electrons, so 2 electrons distributed in those 6 possibilities, so that's what the 2 represents, and that's how I use that formula for the combination to give me 15. But if you just did this by hand, you could probably work out that there are 15, and assuming you don't miss one by not being rigorous here. But you would see, for example, that you could put 2 in this orbital, you can see you put 2 in the middle orbital, put 2 in the last orbital, and then you put 1 here, 1 there, 1 there, and there, and then you can start varying up and down. So you just try to exhaust all the possibilities until you've written them all down, do some systematic way, and then you've written down all the possible sort of configurations here. Now, what we want to figure out is what are the terms that are associated with a 2p2, and can we identify which of these configurations could be associated with which of the terms? All right, so the answer's already up there, but we're going to work through that here. So just don't worry about this. We're going to figure out how that comes about. But you can see right away that now that we have this sort of diagram built, we can start calculating things. Like we can calculate the total m sub L. And since, like, for example, here we have -1 for m sub L, and we have 2 electrons in that state, none in the others, then that gives us a total m sub L of -2. And since this spin is up, that spin is down, m sub s is canceled, we have m sub s of 0. And then when you add them together, you get m sub j, which is m sub L plus m sub s, you get -2 there, all right? So just focus on this column here, filling these out. So just look at every one of these guys and add up the electrons that are in the m sub L. For every electron in the m sub L, take that value and multiply it times the number of electrons in that box, and you should get these m sub L values here. And then count the number of electrons that are up minus the number of electrons that are down, and that will give you, 1/2 times that will give you all of these numbers there. So that gives you, so it's plus half, minus half, 0. If it's plus half, then plus 1. Yeah, so what I said was right. So anyway, once you do that, then you can add up all of these columns. So that gets you more or less right to this part right here, and you've done all of that. Okay. So hopefully that part makes sense. Okay, this is a classic quiz or exam problem. Now, just like we did before, we're going to look at these values and try to guess what are the total S, L, and J values that are present in this system with 2p2. So when we look at the m sub L's, we see there's a -2, there's a +2. So clearly, to get to plus or minus 2 for m sub L, we must have an L equals 2 possibility, right? So that's the only way that can happen. Now when you look at that -2 here, and you look at that +2, it's associated with an m sub S of 0. Now, if there was an S value associated with this guy that was greater than 0, then we would expect to see -2 associated with plus or minus 1, for example, if S was equal to 1. But we only see these two values, -2 and 2, associated with m sub S of 0. So that tells us that this L equals 2 must be associated with an S equals 0. So 2 plus 0 is going to be a J equals 2. So there we have it. We know that L equals 2 is a D, S0 is a singlet, J2 gives us 2, so singlet D2, that has 5 states associated with m sub L, -2, -1, 0, +1, and +2, all associated with m sub S of 0. So when you look in that list, anytime you see something that's consistent with this state, we're just going to put, there it is, D1, here's 1, that's consistent, D1, D1, D1. Now, if you put these guys 1, 2, 3, 4, 5, 6, 7, 8, 9, but as we said, there's only 5 states. So what's happening is that these are all the ones that are consistent. These 5 states actually will end up being linear combinations of these states. So, all right, this is a moment where you have to go back and look at that chapter where we first talked about angular momentum, and we talked about how to represent the states with given m sub L and m sub S in terms of m sub J, and using Clebsch-Gordan coefficients, and you would have seen that you can write the J, m sub J state as some linear combination of m sub S and m sub L states. So that's the reason why there's going to be more D's labeled over here, because these 5 states are going to be linear combinations of these guys over here. Okay. So with these 5 states eliminated, so that means that we know that out of the 15 states, that means that there's still 10 states that we have to sort of attribute to other possible capital L's and capital S's. So then we can look at this and we can see that the next largest term for m sub L, so here you see an m sub L, it's -1. Here you see an m sub L, it's +1. And you see it's associated with +1 for the m sub S. Here you see an m sub of L is +1, and m sub L of -1, and it's associated with -1. So what's looking like, and here you see m sub L plus or minus 1 associated with 0 also. So what it's looking like is that we clearly have an m sub L telling us that there is an L equals 1 state associated with an S equals 1 state. So we have m sub S of -1, 0, and +1 associated with m sub L of -1, 0, and +1. So that means that the J states that we're going to get are going to be the difference, J equals 0, all the way up to the sum, J equals 2. So 1 minus 1, which is 0, to 0 to 1 plus 1, which is 2, and everything in between. So 0, 1, and 2 are going to be our possible J states. Again, this is a consequence of the uncertainty principle, that we can't add our vector components because we only know 1 out of 3. So we have to allow for all the possibilities for the addition of angular momentum. So these are our possible states. So that means that we're going to have, for L, we're going to have P's. For S, we're going to have 2S plus 1 triplets. And for J's, we're going to have 0, 1, 2. So we're going to have triplet P0, triplet P1, and triplet P2. All right? And each of these guys is 3 states, 3 states, and 3 states. So that's a total of 9 states. So we just accounted for 5. Here we account for 9. And we have 15 total, so that means there's only 1 left. So then the only way you can have that is to have a state that's S equals 0, L equals 0, and J equals 0. So there's a singlet S0 in there also. So, and again, all of these guys, all the ones that are possible linear combinations of this guy are this one right here. This is singlet S0, this is singlet, and this is singlet S right here, okay? So all of those guys are labeled there as possible terms that will be associated with linear combinations of those guys. So here we go then. We're down to the wire here. What we have left then is to figure out, of all those states, singlet D2, triplet P0, P1, and P2, and singlet S0, which one is the ground state? All right, and what we find is, well, the ones with the highest multiplicity, which are these guys, are going to have to be the ones considered. And now we have to look out amongst the different J's to figure out, and in this case, it's less than half filled. So the subshell is less than half filled. So we're going to take the lowest J, so that's going to be this guy. So triplet P0 is the ground state for 2P2 configuration. All right? And again, triplet P0 will be some linear combination of these guys. And you'd have to work that out with, say, Clebsch-Gordon coefficients. But to identify the ground term symbol, we've done everything we need to do here. All right, there are a lot of problems like this, and these are sort of classic PChem spectroscopy problems. So we haven't been talking about multi-Z atoms, high Z atoms for multi-electron ions, but let's just say a little bit about this because I'm not going to go much into this. So once we get up to high Z, the spin-orbit coupling becomes much bigger than the electron-electron repulsion term. So in this case, we're going to calculate the total angular momentum. It's more convenient to calculate it as the sum of the individual J's. So for each electron, we're going to calculate the individual electron's J by taking its individual orbital plus spin angular momentum, and then we're going to take those J's and we're going to add them up to make the total J. That's the way we're going to do this. And we're going to find that this 0th order Hamiltonian commutes with J, so this is a constant of motion, and actually you find that these individual J's are also constant of motion. So that's what makes this way of doing it sort of the smart way of doing it, because you've identified the variables that are the constant of motion. But on the other hand, if you went and calculated the total L or the total S from the individual electrons, you'd find that those operators don't commute with this guy, okay? So we got rid of the repulsion, replaced it with spin orbit. This 0th order Hamiltonian I'm calling H02 for the high Z case. That guy doesn't commute with L and S, which means the total orbital angular momentum, spin aside, just the total orbital angular momentum is not conserved in this case. So that's going to be changing with time. And the same is true for the total spin angular momentum. But J, of course, is conserved. So these guys are not separately conserved. So in this limit, where this is the case, this is what's called the JJ coupling limit, all right? Term symbols don't work because term symbols are defined with capital L and a capital S. So assume that those guys are relative constants of motion. So there you go. We're not going to use term symbols. We're not even going to treat this case. There are some approaches that people do, sort of use some term symbols, but we're not going to get into that. Let's just stick with the lower 40 for this class. Okay. All right, so that's it for term symbols. All right, so now you have some homework problems. You can take a look at those. And we will then, probably you'll see those on the final exam. And now what we're gonna be looking at is just one quick thing at the end of this chapter, which is, as we start adding in all of these particles, and maybe even start talking about molecules and having more nuclei in, the equations are just gonna get so big that they're not even gonna fit on the page, and we're gonna have troubles. But there's another reason for wanting to do this, changing things here. So what we're gonna do is we're gonna switch over the Schrodinger equation into a dimensionless Schrodinger equation, so every variable is expressed as some dimensionless variable, which is some ratio with an atomic scale unit. So what I'm talking about is this. So let's take, for example, this potential energy term, okay? Q is a fundamental constant, Z's, the charge, all right? And we put this all into Schrodinger equation and it looks something like this. Now these numbers are all really, really tiny, right? This is like 10 to the minus 34, right? And these charges are all these numbers, if you just worked on standard SI, base units, these would be really tiny numbers. You wouldn't be plugging those into your numerical calculations, because you'd probably start ending up with all kinds of round off error because you're using such tiny numbers. So you would like to sort of scale things up in a way that's sort of intelligent here, so that you were working with sort of normal sized numbers that didn't have any kind of round off errors. So one of the things that chemists do first off is to say, well, let's just talk about all the distances in terms of Bohr radii. So we're going to define the Bohr radius as the atomic unit of distance. So that's our ruler on the atomic scale. The little tick marks are going to be in steps of Bohr radii and our atomic scale ruler here for distance. So we're going to take, what we're going to do is we're going to take all of our r's and we're going to divide them by that, and we're going to represent, this is a dimensionless r. So when you see this dimensionless r, it means that just multiply that times the Bohr radius and you'll get a dimension-full quantity, all right? So if I do that, if I go back to the Laplacian and I convert it into these units, so in other words, if I do that multiplication or division here, then the Laplacian ends up being converted into this, where now x, y, and z are also dimensionless quantities. Okay, you should check this. And then when you convert the wave function, it's, the probability is psi squared dr, and then we're going to change that to psi squared dr prime, psi squared function of r prime dr, and then we're going to sort of rearrange this, and we'll see that we can rewrite this guy like this. So finally then, we go back to the Schrodinger equation, written in terms of a wave function in terms of a dimensionless r, is going to look like this right here. And so now you see these A naughts that show up here that you need to sort of keep everything clean. But we're going to keep working on this. So then what we're going to do is we're going to take the atomic unit of energy and say, well, if we did that with r, and we made it dimensionless in sort of steps of Bohr radii, why not just do it with energy too? Energy is in terms of Hartrees. So this is a Hartree unit of energy, which I can also, you can check this, you can express it this way. And if we go ahead, and since assume we're working with heavier atoms, we can make this assumption, then we can convert that previous expression cleanly into this by just multiplying it like that through. And then we can take it one step further by taking all the energies and scaling them by Hartrees, and we end up with that expression. All right. So at this point, we're just going to stick with this, but these R primes, E primes are just becoming a pain in the butt. So what we're going to do is just drop it, and the assumption amongst all the computational chemists is, of course, we're working in atomic units. All of our variables are dimensionless, and they just need to be multiplied by the appropriate atomic scale unit to bring them back to dimensionful units. So R is dimensionless, E is dimensionless, but you just have to bring them back by, when you're done with your calculation, to a number that has dimensions. So in other words, here's all the quantities that you might be interested in. So if you get an output from some computational chemistry program and you get an energy, there won't be a unit on the energy. Maybe they'll convert it for you, or angular momentum, or electric polarizability. If they're given to you in atomic scale units, you just need to multiply them by the corresponding factor, which will then convert them back into a dimensionful unit. But then the nice thing is, if you work in this dimensionless atomic units Hamiltonian, then the multi-electron atom then looks like that. So it's much more concise, and you just get used to it, and you don't think about it anymore. And we'll pick up and use this for the last chapter. All right. And I think that's it for this chapter. Okay.